derivatives, so we'll be doing derivatives until after Christmas. So what we were doing, and I kind of already talked about, like last section they had us doing this, and they used a because most of the time we were plugging in a particular value. But in general, we're going to want a formula for the derivative, not just the number at a particular x value. So most of the time from now on, they're going to keep it with x's, which I told you guys in the last section, you could go ahead and just start using x's instead of a's, so we didn't have to switch our notation as we went through this. We know what is f prime of x. What does that represent?
The change at f(x).
Right. It's a derivative. It represents the rate of change in our function f of x at a particular point. On a graph, what does it represent?
Slope.
Of?
Rate of change.
The tangent.
The slope of the tangent line. Yes, a slope is a rate of change, so it is a rate of change. It's the slope of the tangent line. So the first thing I want to do is draw a derivative. Okay, so that's something we've never done before. But we can think. You okay?
I just got water all over my paper. It's all wet now.
Well, Ben knows how to deal with that. What do you do when your papers are all wet, Ben?
You put them on the floor and wait.
Okay. Did they all dry out? You never
Mostly.
asked me to make copies.
You probably can't write on them very well.
Okay.
It's only one.
So let's start with some easy things. Right here, what would the slope of the tangent line be? I drew the tangent line.
How do you know it's right there?
What do you mean? Like, how do I know that's what the tangent line looks like?
Yeah.
Because the tangent line only hits it once. It's like following the shape of the graph. And so anytime we have this high or low point, our tangent line is going to be just a flat line. So these tangent lines are horizontal. What is the slope of a horizontal line?
0.
0. So if I'm graphing the derivative is the slope of the tangent line. At these 3 points, the tangent line would be horizontal, so it would have a 0 slope, so the derivative is 0.
Wait, so the tangent line can't be like diagonal?
So it will follow the shape of the graph. So like right here, it would be diagonal. Here it's kind of flattening out. And it's becoming horizontal there. So let's look at those. What's true about all of these slopes? What do they have in common?
They're negative.
They're negative, right? Those were all decreasing, so they had negative slopes. So our derivative would be negative there. Okay, without finding like exact points, all I know is from where I started until here, my derivative was negative. All right, what's going to be true about the tangent lines after that? These are all positive slope because they're increasing. So now my derivative is positive until I get to here. So we have a lot of work to do on figuring out what the graph does, but we just know that it has to be positive the whole time. Okay, we don't really know necessarily where it peaks yet. I'm just looking, do you have your zeros in the right spots, your positives and negatives in the right spots? And then what happens from here all the way down to there? Yeah, the graph was decreasing, so the tangent line is going to be negative the whole time. We have to come back and hit 0 here. So it's something like this. And then from there on forever, what's true about my graph?
It's on the rise.
Yep, it's on the rise, so my derivative will be positive. Now, is this a great graph? No. And we will keep talking about different things and tweak this idea as we move on and learn more about the derivative. But right now, what you should be able to know is that any time the tangent line is horizontal, which happens at maximum and minimum points, the derivative is going to be 0. If the function is increasing, the derivative is positive. And if the function is decreasing, the derivative is negative. So let's practice finding a derivative. You guys did that on the homework we turned in. Found lots of them. So I have a function, f of x equals x cubed minus x. So I want f prime of x. So the derivative, that is the definition that we've been using, the limit as h approaches 0. F of x plus h. So x plus h cubed minus the x plus h minus f of x. What is f of x?
X cubed plus minus x.
All over h. Alright. So then, we can start multiplying things out. X plus h cubed. That's x cubed plus 3x squared h plus 3xh squared plus h cubed. Are you guys okay if I just write down what that is?
Yeah.
We worked it out yesterday, multiplied out one. Minus the x plus h, so we just distribute the negative, so minus x minus h. Minus the x cubed minus x, so minus x cubed plus x. What happens?
Put the x's and the x cubed. And the h.
Alright.
Not the h.
Well, we can reduce an h out of everything. So we get 3x squared plus 3xh plus h squared minus 1, because I had a plain h up here, and h divided by h will be 1. Then if you plug in zeros for all of your x's, or sorry, for all of your h's, what do we get? 3x squared minus 1. Alright, so that's the derivative. Let's use our graphing calculator real quick and just compare the graphs of these two things and see if they're kind of related the way we predicted. So my original was x cubed minus x. And my new one is 3x squared minus 1. So that's the original, the blue one. Notice it started out increasing, so I would expect my derivative to be positive. I hit a maximum, so my derivative should be 0. Switched to decreasing, so my derivative was negative. Had a minimum, so derivative was 0 again. And then it was increasing, so my derivative was positive after that.
Oh. Just kidding.
You're right.
Yeah, I think I put in a 2 instead of a 3. Or like I put in a square cubed instead of square.
Oh.
So my graph was weird.
So we see this follows the same rules we kind of talked about on our last graph, where we have the zeros and then where it's positive and negative. All right, let's keep doing derivatives. That's the majority of what we're doing in this section, is working through those derivatives. So if my function is the square root of x, so my derivative, f prime of x, the limit as h approaches 0, f of x plus h, so the square root of x plus h, minus f of x, so the square root of x, all over h. What should we do here? So we have the square root of x plus h plus the square root of x and the square root of x plus h plus the square root of x on the bottom. So on top, square root of x plus h times the square root of x plus h, that's just x plus h. Outside and inside cancel, radical x times radical x minus x. What happens? X's cancel. Then I have h over that. So I could go ahead and reduce an h. So if I plug in 0, I get 1 over 2 square root of x. Technically, is that proper notation? No. We are going to, I don't know if I should even say this. I'm going to allow you to be a little bit lazy when we start doing some of these derivatives. We are not going to worry about getting radicals off the denominator right now. The reason being, well, A, I know that you know how to do that. I know that you know to multiply by square root of x on top and bottom. But B, eventually we will do like second derivatives and third derivatives, and those are easier the more simplified our answer is. So those are easier from here versus when I have the square root of x over x. So we're going to just leave it like this for now. I also did ask you a question. What's the domain of f? The original function. What can, if you have a square root, what kind of numbers can be under a square root?
Oh, only positive.
Can you do the square root of 0? Yeah. So the original had a domain of 0 to infinity. The 0 had a bracket because you could put in the 0. What is the domain of the derivative?
Negative positive.
We still have a square root, right? So we can still only have positives.
Yeah.
Can you plug 0 in? Why?
Yeah.
We can do the square root of 0, but can we do 1 divided by the square root of 0?
No.
So the domain of the derivative here, you can't have 0 in it. So just a good thing to discuss periodically. Domains are important when we start drawing graphs and pieces like that. So we'll try to incorporate them here and there along the way. The next slide, I just have the pictures of the original and the derivative. And so you'll notice, does this original ever have a maximum or minimum? No, so the tangent line is never 0. So the derivative never hits 0. It's increasing the whole time, so the derivative is always positive. But you'll notice it starts out increasing pretty quickly, and then what happens over time? It's flattened out. So what happens is the derivative starts out pretty high because the tangent lines are steeper, they have a bigger slope, and as those lines get flatter, the derivative is getting smaller. Okay, so we will look at that more, but just starting to talk about those pieces. when we look at them. What happens is with that graph, we're actually getting a horizontal asymptote. And we already know, how do you find horizontal asymptotes exactly?
So the bottom zero.
You do the limit as x approaches positive infinity and the limit as x approaches
Oh my gosh.
negative infinity. We did that in our last test. Okay, let's take a look at this one. I want the derivative. So, same thing again. Limit as h approaches 0. F of x plus h. So that's 1 minus x plus h over 2 plus x plus h minus f of x, 1 minus x over 2 plus x all over h. I'm going to rewrite this. And if you just wanted to switch it in the original, you can, but I'm going to go ahead and change that to 1 minus x minus h. And I'm just going to drop the parentheses on the bottom here. Alright, so we had some like this on our homework. What do we need to do?
Multiply by 2 x plus h and 2 plus x.
Got to get a common denominator. So this one needs 2 plus x on top and bottom. This one needs 2 plus x plus h. Alright, so we start distributing. So 1 times 2 is 2 plus x minus 2x minus x squared minus 2h minus xh minus, and I multiply those through, 2 plus x plus h minus 2x minus x squared minus xh. All over 2 plus x plus h times 2 plus x. Can I go ahead? This is divided by h. Could I write times 1 over h so I don't have a fraction and a fraction anymore? Okay. How do we go about cleaning up this mess?
Cancel stuff.
Okay, if we distribute this negative, positive 2 and negative 2 cancel, positive x, negative x, negative 2x, positive 2x, negative x squared, negative xh, positive xh. So I'm left with negative 2h minus h. Now what happens? And so then we can plug in a 0 for h, so we get negative 3 over 2 plus x times 2 plus x, or negative 3 over 2 plus x squared. Okay, as the day goes on, there's a delay in my board. Have you guys noticed this lately? Like I'm writing, but it doesn't keep up there, so I have all these random little.
It's
it's a pain. It bothers me.
My brain's very, that
My board.
so the
Keep
board
up.
is gotta struggle a bit too.
So that's our derivative. These should seem kind of familiar because you had problems like all of these on last night's. And that's kind of why I went ahead and had you start using x's instead of a's then, so you would realize this is just the exact same thing. We're still practicing the same skill. There are a lot of different notations that mean derivative. So I want you to be used to seeing all of them. Typically what I've used is f prime. If your function is just, if it's y equals something instead of f of x equals, we could call that y prime. A lot of times you'll see me use dy dx. Df dx, you could have a d over dx and an f of x up to the side. They could have capital D and f of x, a d sub x and f of x, a lot of different notations. You will see me using these first three. All of them mean the same thing. Find the derivative, find the slope of the tangent line. That's all we're doing here. We will get to the point where, like the ones you were doing last night, you had to find the equation of the tangent line, so you had to do the derivative and plug in a specific number for x. So a shorthand you might see is dy dx meaning the derivative and a vertical line and then x equals some number. And that means do your derivative and plug in this number for x. So that's another notation that we will see. So I think this is might be where I stopped today. So if a function is differentiable, that just means we can find the derivative. Okay, so if it has a derivative, it's a differentiable function. It may be differentiable on an open interval, not the closed interval, like that example number 3. The original function, the square root of x, we could have a 0, right? But could I have 0 in my derivative? No. So it was not differentiable at 0. The derivative didn't exist at 0, but it existed everywhere else. What I want to do, we're going to kind of skip to the back, and I want to look at a couple problems. So I pulled a few problems out of the textbook. So this is problem number 2. Problem number 1 is on your homework. So I'm kind of doing some out of the textbook, very similar to what I have assigned you. So this one, in the book, it says use the graph to estimate the value of each derivative. So we have to figure out what each of these derivatives will be. Okay, I say estimate because it's hard to do this exactly. As long as you're in the ballpark, I'm going to give it to you on these, but we're just going to do our best to try to figure out what they would be. A ruler might be helpful to you on this. Let me get some rulers out.
Does Miss Keller have these?
Yeah, she stole it from us. All right, so the first one, f prime is 0. It's asking me estimate what the derivative is when x is 0. So what we have to do, we know the derivative is the slope of the tangent line. We are going to do our best to draw a tangent line at 0. Okay, I say do our best because it's not going to be perfect. Tangent line follows the shape of the curve, pretty much only hits the graph at that point. It's probably easier for you guys to draw this than me because I can't lay a ruler on my board because that's thin it. Yeah. So you guys are going to have to be the accurate ones here because I can't. So you need to take your ruler and try to draw a tangent line here. It's probably going to look something like this. Maybe not quite that steep, but we know it's going to have a positive slope, right? We're trying to hit our graph roughly there. And then we are just going to estimate, and I say estimate because it is not perfect, the slope of this line. So this one, it looks like if I went from here to here, I would have to go up 2 and over about 1/3. Rise over run. So 2 divided by 1/3 will give me a 6. So my slope of that line is roughly 6. So that is roughly my derivative. All right, at 1, if you draw your tangent line at 1, what kind of line do we have? Horizontal. So what's the derivative at 1? 0. Okay, at 2. First of all, is this going to be a positive or a negative? Negative. So draw the best you can, hits the graph at this point, and then take 2 points on that and see if you can calculate slope. So if I took these, it looks like I go down 1 over 1, so 1 divided by -1, roughly a slope of -1. It's not exact, but ballpark. At 3, what kind of slope would this line have? Should be negative. Again, you guys are probably having a little more success using your rulers here. So take a couple points on that line, calculate rise over run, so down to what do you think? What are you guys estimating? You sure you can? About -2, probably anything between -1 and -2 is close, somewhere in there. All right, 4. So this one, it's still negative, but it should be getting smaller, right? Can you see that the graph is kind of flattening out here? This line is a little less steep than the last one. So what do you think for that slope? About -1, probably something in that ballpark to work. At 5. Okay, so if I drew my tangent line at 5, I think like -1/3 about. What about at 6? That one should be a 0. And 7, this one's increasing. You think about +1/3 roughly?
Yeah.
So I'm giving you one of these on your homework. I'm not expecting any like amazing results here, just kind of a general, just really wanting you to make the connection. A derivative is the slope of the tangent line at that particular point. Do your best kind of drawing those tangent lines and estimate your slope. All right. We could use these points to kind of draw a graph of our derivative, because this gives us essentially ordered pairs on our derivative. So the first point I have is 0, 6. I have 1, 0. 2, -1. 3, -2. 4, -1. 5, -1/3. 6, 0. And 7, +1/3. So my graph is something along those lines. It should be curved. It's not like we didn't have any sharp corners or anything, so it should look something like that. Any questions on that one? I want to do one last homework type problem today along with the graphs, and then I'm done for today's portion. So the next one, this is question number 6 out of the textbook. And when you get to this, the directions are to graph the derivative. So if I'm trying to graph the derivative, what's the easiest thing to graph? We've got, here, my graph would have to be 0. We notice this graph is flattening out, so it's kind of got a horizontal asymptote going on. This whole time, my function is increasing. We look right here, it's pretty flat, so it's going to be a pretty low positive value, and then what happens to it? Yeah, it's increasing way faster, so it's going to actually kind of spike and come back down. So it's flattening out here because the graph is flattening out. We have to go up, but we have to come back down to hit the 0. This one is decreasing, starts off decreasing pretty quickly, but then we've got to come back to our horizontal asymptote. So the derivative looks something like that. Okay. So we will practice more tomorrow and keep working on this section. Homework-wise, this is the homework for the entire section. Because several of them ask for the graphing and it's kind